here we go again. Like, the story of the stellar corpses would not be strange enough if it ended with white dwarfs and the neutron stars. Now there is yet another, actually even more bizarre, if not the most bizarre type of object in the universe, a black hole. That happens because the gravity in a stellar corpse becomes so strong that nothing can prevent the corpse from collapsing under its own weight. So that stellar corpse collapses without end, crushing itself into oblivion, out of existence, and forming this exotic, bizarre thing where nothing, not even the fastest thing that exists out there, can escape from. All right, so we've seen that the neutron star is the endpoint of the life in a very massive star, or massive star. But if that star is actually very massive, the core is going to have more matter than in 3 suns put together. And so in that situation, not even neutrons can support the weight or the neutron degeneracy pressure, to be more exact. All right, so gravity wins, totally wins. Okay, so before we understand how things like this can happen, let me have a question for you. What do you think happens to the escape velocity from an object if you shrink it? Okay, what do we mean by escape velocity, right? It's like the speed at which one would have to be able to travel in order to win over the pull of gravity. Okay, so it's the velocity needed to pull away from the force or the pull of gravity. So what do you think is going to happen if you shrink that gravitational, the object that exerts that gravitational force on you? If you shrink it, what do you think is going to happen? Do you need to travel faster? Do you need to speed up? So increase the speed, the velocity, or decrease, or it's probably going to stay the same. What do you think? First of all, the hint comes from remembering what the force of gravity is about. Remember how that is proportional to the masses and inversely proportional to the distance. So now shrink it means the distance between those two objects decreases. If the distance decreases, the distance square decreases even more. Actually, the square of whatever the decrease was before. So that's a lot. And if the square decreases, that means the force of gravity is going to, what do you think? Increase, right? Because you're divided by something smaller and smaller and smaller. And when you divide by something small, you obtain a really high number, higher and higher number. So if the force of gravity is going to become stronger, what do you need to do in order to escape that pull of gravity? You're gonna have to speed up, basically. Okay, so here's how the escape velocity is calculated, and we're gonna need that in order to understand the size of a black hole, or as we will see, the black hole, it doesn't really have a size, but it is a surface in quotes. about that black hole, any black hole, in fact. All right, so basically, anything would escape as long as the kinetic energy is going to be at least, right? So it could be like this, but it's at least equal to basically the gravitational potential energy corresponding to the pull. Okay, and you might remember the kinetic energy has the formula mv squared over 2, and the gravitational potential energy has the formula G, being the universal constant of gravity, the mass, that is the big mass of the object that exerts the pull, and the little m. So you see these cancel, and so you end up with v squared escape divided by 2 equals with G m, the mass of the object that exerts the pull again, and the radius. Okay, so at some point, right, if m is large, v escape is going to be large as well. The largest v escape is going to be the speed of light. There is nothing faster in this universe, nothing faster than the light, okay? Remember the value of that speed, 3 times 10 to the 5 kilometers per second, or 3 times 10 to the 8 meters per second. Okay, so what's going to be the size of that object of mass m for which, so now if v escape is actually the speed of light, let's plug it in, okay? So we're going to have c squared divided by 2 equals g m over r. Solve now for r. So we're going to have r equals 2 g m with the 2 in front divided by c squared. So we find the size or the radius of the distance from that singularity or the black hole where there is no return, right? And that is called the event horizon, that situation, if you want, so something like that. So this is the black hole, and we have the Schwarzschild radius here, and we're going to call this event horizon. So that's the distance from the black hole where r, where v escape is the speed of light. Okay, and we just calculated that Schwarzschild radius as being 2 times gravitational universal gravitational constant times the mass of the object, in this case it's going to be the black hole, divided by the speed of light squared. And this is going to turn out to be a very useful formula. In fact, you can use that to even calculate how big of a black hole, or basically how large or big is, or what's the radius of an event horizon of you being a black hole, like your whole mass. If your whole mass would have the ability to crush and become a black hole, how big of a black hole that would be. So you can calculate that now. Okay? All right. So how big is it? This doesn't look the way I want it. Okay, so let's try something else. So the neutron star was the size of a small city, Well, guess what? The event horizon of a black hole of, say, about, right? So event horizon of a black hole of mass m black hole about 3 times the mass of the sun is going to be just a little bit smaller than a neutron star of close to almost 3 solar masses. Okay, so as big as a small city, just a little bit tinier than that. So again, right, that is just, right, so the black hole would be here somewhere in the very center. This is the radius, the social radius, or the radius of the event horizon. It's not, so we can call it a size, but it's not really a size per se, right? The black hole is a singularity. So the black hole is, it is a point. However, that is defined. Okay, now the black hole has some strange properties. All right, so let's think about that. For example, we have here a, say, flat, a two-dimensional representation of a flat space-time. Now you add a mass. If that mass is particularly large and its size is particularly small, well, that mass will affect that kind of rubber sheet similarly to the way actually gravity curves space-time. Einstein came up with this genial idea, of course. And look at how the circles become more widely separated as we move closer to the mass. Like this distance is actually larger than this distance. And here, when there is no mass to disturb that space, time is pretty much the same radial distance between. So this is equal to this, right? This is larger than this. And this would be the event horizon. So say instead of just a mass, now here is the black hole. Okay, look at how much the space is curved. Okay, so the curvature of the space-time becomes greater and greater as we approach a black hole. And the black hole itself is a bottomless pit in space-time. So, a black hole's mass strongly warps space and time in the vicinity of the event horizon. Another very interesting thing is that there is actually no escape. Once you're inside the event horizon, there is actually no more contact with the thing, anything. That's something that falls in. Okay. Yes, it's going to add to the mass of the black hole. It's probably going to change the spin or its charge, but otherwise it loses its identity. And most of all, we from the outside of the black hole, we're not going to hear about it at all, right? Because not even light escapes. So nothing actually is going to have that power to come out of the black hole and tell us the story. So everything that we know about black hole is going to happen in the vicinity of the black hole. All right. So that is close to the black hole, and close to the black hole, there are some other things that happen, and we're going to go into a bit more detail about it. The time dilates, passes more slowly, and the lengths stretch. For example, light with its wavelength, any kind of wavelength is going to become longer. That means redder as it tries to climb away from the strong gravity. However, right, so this is close to the black hole, but far away from the black hole, gravity acts normally. The text got blended here and messed up. So normally, that means the black holes don't suck. If you're far away from a black hole, really all it can do is just act with its force of gravity. Okay? Whatever that magnitude of the force of gravity is going to be once you apply that formula from Newton, right? It's always going to be inversely dependent on the square of the distance, say, between you and the black hole. So here's a question, not a question. What do you think? Is it easy or hard to fall onto a black hole? Easy, hard. We just said black holes don't suck. That is, especially if you're not close to one. So we also have a hint here. A black hole with the same mass as the sun wouldn't be much bigger than a college campus, right? So think about how vast is this space. Vast. Huge compared to college campus, right? So this is tiny. Actually, extremely. Compared to, for example, the distance between the sun and closest star to the sun. Remember, that is a few light years. That's a lot. That's orders and orders and orders of magnitude larger than the college campus. So basically, it turns out it's actually pretty hard to fall onto a black hole because it's just so much space by comparison out there, right? So it's very hard to actually get to encounter and be very close to the event horizon of that black hole, any black hole, right? So for example, we have the sun and we have the orbit of the Earth around the sun, and remember this 1 AU, 1 astronomical unit distance between the two. And say if by some kind of miracle the sun is going to be replaced by a black hole that has the same mass as the sun, what do you think is going to happen to the Earth? Well, to the Earth itself, lots of things are going to happen because they're not going to have the light and the warmth and the beautiful shine from the sun itself. But the orbit of the Earth will not change a bit. Nothing will happen. It's the same mass, right? It's the same mass that is going to keep in orbit everything that the sun keeps in orbit. So in that sense, the black holes don't suck. All right, so I said we're going to talk in a little bit more detail about what's happening when we're getting closer to a black hole. So he said the time passes more slowly near the event horizon, right? So time dilates. Google up the twin paradox, if you wish. It's like you and your twin, one of you stays on the surface of the Earth, one of you, by some kind of magic, ends up close to the event horizon of a black hole. And the one that's close to the event horizon of a black hole is going to spend maybe, an hour or two, just hang out there, see what it's like. And then say it has the ability or possibility to come back to its twin. Well, it turns out, right, because the time ran much more slowly closer to the black hole, it turns out when it comes back to the Earth, on the surface of the Earth, time flew much faster and its twin either died or, I don't know, maybe there were a few hundred years passed while the twin closer to the black hole seemed like just a few hours. So something like that. All right, another thing. So that's one. Another thing is that there are strong tidal stretches forces. Okay, so what do we mean by that? Look at the feet. Okay, so feet are closer to the event horizon, to the black hole. So closer means smaller distance, right? D square even smaller. So the force of gravity that acts on the feet is going to be strong. Much stronger than, say, the gravitational force that act on your head or on your hands, right? So smaller gravitational force because the distance is larger. Okay, so you see there is a differential force, right? So you're going to be pulled much stronger by the feet and not as strong or less strong by the hands. So basically, you're going to be spaghettified. Maybe not you. Maybe you're going to throw something else onto the black hole, and that thing is going to be spaghettified because the length of that thing is going to stretch, and the side of the object that is perpendicular to the length, the width is going to be squeezed. All right, and of course, all those tidal forces, these tidal forces are actually smaller for larger black holes, but you're still gonna see or feel the spaghettification effect. All right, so that happens to the light itself as well, right? Or actually to the light or to its wavelength. Okay. So the light waves are going to take extra time to climb out of a deep hole in space-time, leading to the so-called gravitational redshift. So I wanted to mention that just in case you're going out to read everything there is out there about black holes. But now, of course, the question you should have for me or for anyone else or in your searches of stories about black holes would be, do they really exist? Do we have actually any evidence for these things being out there? And actually, is there any way we can measure just how much mass is in those things? I mean, they're dark, we don't see them, right? How do we know that these things exist? Now, the beauty of these things is that we can guess, we can estimate that mass that produces these effects, like keeps things in orbit or modifies their orbit, it curves their orbit. So there are some things that, it doesn't seem like it's anything out there in space, in the universe, and yet we see the effects of that huge mass that comes from a tiny, tiny volume. And so we basically look at those effects. If we're gonna see things that orbit, like we do see stars, for example, orbiting a point in the center of our own galaxy that does not emit light. Okay, so there's a point there, and all the calculations point towards one point. Okay, and what we can do there is measure the orbital properties either of a companion star, or in the case I just mentioned, the orbits of stars, or stars that orbit something that we don't see. Okay, so we either measure velocity or distance or period of rotation or orbital period. And then use Newton's version of Kepler's third law, and we can calculate the mass. So do that. Remind yourself what the Newton's version of Kepler's third law is, and see if you can actually, figure a way to calculate the black hole masses. This is basically how we do it. And we do have good estimates for those masses that do stuff, all right? And in particular, we have evidence for stuff that is done to the companion, like in here. So here's the companion star, as this is a binary star system. And we do see an X-ray burst. Remember? We talked about that. And usually you think, okay, that is because maybe there is a neutron star here and there is mass transfer. And then because the friction here is going to heat up, and we're going to have here, it's going to be hydrogen that fuses into helium, and that's what's creating, the new light emission that's happening at very high energies or very high frequencies in the X-ray part of the electromagnetic spectrum. All right, so some X-ray binaries, just like the ones I described just now, some X-ray binaries, actually for some of these, they contain compact objects of mass exceeding 3 solar masses. How do we, right? So we calculate the mass of the central object, and we find out that that is at least 3 times the mass of the sun. And then we know the only thing that can actually exist with that kind of mass, that could have been a neutron star, that is going to be, right, so central object is a black hole. There's no other explanation, no other scenario that is going to explain what's going on, the properties of the things that we observe there. And one famous black hole in our own galaxy is actually found in a Cygnus constellation, and it's right about it. It's called Cygnus X1, and that is because it's the first X-ray source that is seen in this constellation. And based on calculations, we know that the X-ray burst that's coming from that binary system needs to be, because there is accretion of matter from the companion onto a black hole. So here are some, let's play some games, some questions. Here's a question. So we have a spacecraft on a trajectory that happens to be taking it near a black hole. This would be the black hole. And here are some scenarios. What do you think? Which one of these diagrams shows how the spacecraft's object orbit will be affected? And the correct answer is situation B. Yes, the orbit will be curved. Okay, but these three won't happen because the angular momentum must be conserved. If the spacecraft basically falls onto the black hole, so falls onto the black hole only if it loses angular momentum. Okay, remember that angular momentum is mass times velocity times the radius of rotation, or the radius of the orbit. And so in order for that to become zero, right, falling onto the black hole, something needs to happen with this whole angular momentum, and there was no information basically in this problem, in this question about, is there any other external force, external circumstances that are going to be able to extract some angular momentum from the spacecraft. So that's why, again, black holes don't suck. They're going to curve your orbit, but that's about it. Really, really close to the black hole in order to be sucked in. So basically very close to the event horizon, which is going to be very unlikely given how small that event horizon is going to be for a black hole. Here's another question. We have a binary system here that looks just like in this painting. This is artist's rendition of a binary system, binary star system with mass exchange, right? You see that? So, and we have here 4 labels for 4 different regions. And the question is, which one of the 4 labeled regions is the source of most of the X-rays? And the answer is 2, because this is where the accretion disk is, right? So here we have friction that's going to heat up gas falling onto the black hole. And if it's heated up, it's going to emit those high energy part of the electromagnetic, high energy light, high energy type of electromagnetic radiation, which are the X-rays. All right, so obviously for more problems, more questions, exotic like these ones, you go to the Mastering Astronomy. You're going to find plenty of them there.